Today we're going to talk about nuclear magnetic resonance, which is NMR. You might see it referred to as HNMR. The one there would indicate that it is the isotope of hydrogen with one proton. In the real world, it is called MRI. So in the hospital, you can go get an MRI so that you can see the inside joints and tissues. That's an MRI, and it's the same thing as an NMR. It's just done on your body instead of on a sample. Down here you can see what the machine would look like. You have magnets, you put the sample in there, radio waves come in and out, and then it produces our spectrum. It's a powerful technique. It helps us find the structure and the shape of the molecule. The sample is placed in that electromagnet. The field strength varies until the radio waves have the exact frequency needed to make that proton and the hydrogen flip and spin. It's called resonance and can be detected electronically and recorded on the spectrum. This machine at the school I went to in UNCA took up its own little office space, and you weren't allowed to wear any metal or bring any credit cards or key fobs into that room because of the electromagnet was so big it would have destroyed those items. So like you could never take your cell phone into that room or it would stop working properly. All right, the hydrogen molecule. In different environments, it will behave differently, so we get different chemical shifts. The number of peaks then corresponds to the different environments that the hydrogens are in. The area under the peak tells us how many hydrogens that are in that environment. The chemical shifts are relative to TMS, which is trimethylsilane, which is what this is, so silicon surrounded by four methyl groups. You can see the data in section 27 of the data book. It gives you what those peaks would refer to, what type of environments would produce those peaks. So when you look at the graph, the first thing you need to do is draw a line down to see what the value is, and then compare that value with the data booklet. Look at how many different environments there are to make sure it matches the number of peaks, or the number of peaks matches how many different environments there are in the structure. If numbers are given above the peaks, it's the number of atoms in that environment. So it's telling you how many hydrogens are in those environments. So here we have a question, an example. We have C5H10O2. So if we draw that out, you would have 5 carbons, 10 hydrogens, so that's 9 hydrogens. I still have 1 hydrogen and 2 oxygens left. So that means 1 oxygen is double bond and then the other is single bond with the other hydrogen. So we have a carboxylic acid. For question number 3 here, it says identify the peak at 11.5. So this peak right here would represent what? So we can look at our data booklet, section 27. Now if you look there, the shifts, there's ranges and some of the ranges overlap, and that's okay. We're going to look for a range of 11.5. And that would fall, there's one that's 9.0 to 13.0. So our 11.5 would fall into there. And that is our COOH. So it's this hydrogen of the COOH that is giving us this peak. And then look at the height difference. We have 1 hydrogen here, and then we have this really tall peak right here. So in number 4, it says state the information that can be obtained from the integration traces in the HNMR spectrum about the hydrogen atoms responsible at 1.2. So it's talking about this blue line here, this curve. of the blue line. So if this is one hydrogen, what is this? Well, since we know that the molecule has 10 hydrogens, we can say that this is the other 9 hydrogens. Now that doesn't mean that there's one environment, but if you look at your data booklet, the CH3 has a shift of 0.9 to 1.0, and then the CH2s have a shift of 1.3 to 1.4. So there's a little bit of an overlap there. Nothing is precise, but they're all grouped together on this particular NMR. Looking at another example, instead of putting the number of hydrogens at the top, they've listed it at the bottom for us. Sometimes you might see it written at the top like this, and that's just telling you how many hydrogens are in that environment. Now this particular compound, C4H8O2, if we were to try and draw the structure, again, we could have a carboxylic acid, or we can have an ester. And so we have all of our hydrogens coming off here. Now you might be wondering, how did you know to draw them like that, and aren't there other isomers? Well, let's take a look at what that IR band is telling us. So if we look at our data table for IR, which is section 26, and you look at the band at 1730, that would be carbon double bonded to oxygen. So this value right here is telling us we have a double bonded oxygen. So that's found in aldehydes, ketones, carboxylic acids, and esters. Well, this cannot be an aldehyde or a ketone because we have 2 oxygens. So it has to either be the carboxylic acid or the ester. All right, now let's look at the NMR information. Well, how many different environments do we have based on our NMR? We have one environment here, we have one environment here, and one environment here. If I look at my 2 structures, we have one environment from the hydroxyl group, and then these would be the same, just like they were in our last example. But in this one, in the ester, you have 3 hydrogens here that are going to be different from these 2 hydrogens, which is different from these 3 hydrogens. How I know that they're different is because these 2 hydrogens are close to this bonded oxygen, which is going to make them shift a little bit farther than these CH2s over here that are just bonded to another carbon. Because these are shifting a little bit due to the oxygen, that will make them different from this CH3 group. And this CH3 group is going to be different from this CH3 group because of the double bonded oxygen here. So that's how we're getting our 3. And if we look, we can match them up a little bit. This is going to represent one of our CH3s because we have our 3 hydrogens. This will represent a CH3 because of the 3 hydrogens. And this would represent our CH2. So that's another way to tell that it is the ester and not the carboxylic acid, because you have to have 2 CH3 groups.